In this video, we're going to look at the first reaction of halogenoalkanes, which is a reaction called nucleophilic substitution. We introduced this reaction in our session in school, but I'm going to go over it again for the benefit of those who weren't here and just for the rest of you for a little recap. So just as a reminder, halogenoalkanes undergo substitution as opposed to addition, which we see with alkenes. They undergo substitution because they are saturated. That simply means they have no double bonds, they only have single bonds. And so there's no room for a molecule to be added to a halogenoalkane. If we have a halogenoalkane, I've just drawn a general one here with any sort of hydrogens or carbon chains being able to be on the positions where there's nothing there at the end of those bonds. If we want to add something to this molecule, we've got to get rid of something, we've got to substitute it. Then we've got this term nucleophilic. What does that mean? That's a new term for us. We've met the term electrophilic before, but the reactions of halogenoalkanes involve nucleophiles instead of electrophiles. Just remember that bit at the end, philic or nucleophile. The phile part just means to like or be attracted to. This nucleo bit, let's have a think what that means. That nucleo bit refers to the nucleus. And if you think about the nucleus of an atom, the nucleus of an atom contains protons, which are positively charged. So nucleophiles are particles that are attracted to positive or partial positive charges. Where does that happen in a halogenoalkane? Well, if you look at our carbon-halogen bond here, our halogen will be more electronegative than the carbon. So we'll see a slightly polar bond here. So our X, our halogen, will be delta negative and our carbon will be delta positive. So that bond is polar. And it leaves that carbon slightly positive and open to attack by a nucleophile, something that loves a positive or partial positive charge. So what will happen is our nucleophile, which we'll have a look at in a second, will come in, will form a bond with the carbon, and as a result, the X will leave. So that's all summarised on the next page. This is page 17 of your booklet. So this reaction of our halogenoalkanes arises from the fact that we've got a polar bond in our halogenoalkane between our carbon and our halogen, the carbon being delta plus. That leaves it open to attack by a nucleophile. So what is a nucleophile? Here is your C, a definition for a nucleophile. It's an ion or a molecule with a lone pair of electrons. That's its criteria for being a nucleophile. It must have a lone pair of electrons. It doesn't have to have a negative charge. It sometimes does, but it has to have a lone pair of electrons. So it's an ion or a molecule with a lone pair of electrons that attacks a region of low electron density. In this case, with our halogenoalkanes, that region of low electron density is going to be our delta positive carbon. So we can see that nucleophiles are electron pair donors. They will donate their lone pair of electrons to form a bond with this region of low electron density. They have to possess at least one pair of lone pair of electrons. They don't have to have a negative charge, but sometimes they do, and they're attracted to the delta positive electron deficient carbon in our halogenoalkane. So let's have a look at a few examples of some nucleophiles. So we've got, first of all, our hydroxide ion here, OH minus. You can see that it has 3 lone pairs of electrons and a negative charge. Cyanide ion, Cn minus, and we'll see the structure of that in a second, but it's basically a carbon triple bonded to a nitrogen with a negative charge sitting on the carbon atom, and it has 1 lone pair of electrons. Ammonia, you can see, is not negatively charged. It's NH3. But it does have a lone pair of electrons, so it can act as a nucleophile. And then water can as well, H2O, it can act as a nucleophile, but it's not a very good one. And then you're just reminded at the bottom of the page, like we mentioned previously, this has to be a substitution reaction when the nucleophiles attack, because when they form a bond with the carbon, something else has to leave. So one group leaves. That's what we call the leaving group, and that will turn out to be our halogen. And that's because halogenoalkanes are already saturated. So the carbon just has single bonds, so if something else tries to form a bond with it, then it's got to break one of its bonds. So as a result of this nucleophilic substitution, we have to have something leaving because it's a substitution rather than an addition. And the atom that's going to leave is going to be our halogen, and that will break away with the electrons from the carbon halogen bond, and it will become a halide ion. So we talk about the halide ion being a good leaving group, so a good leaving group. Turns out that as we go down the group, the halogens group, the halide ions become better leaving groups, and that's because the carbon halogen bond is increasing in length and becoming weaker, and we'll demonstrate that experimentally later in the topic. So with nucleophilic substitution, it is a mechanism that you need to know and you need to be able to draw, but I think it also helps us in understanding what is happening here in terms of the movement of electrons. So if we draw first of all just a general halogenoalkane, like we had done previously in this video, what you must show is your delta positive charge on your carbon and your delta negative charge on your halogen. We'll then also draw our nucleophile, and it must be shown with a lone pair of electrons. I'm just going to draw it there, but you can draw the lone pair after the U if you prefer. And I'm going to give this nucleophile a negative charge, but remember it doesn't necessarily have to have a negative charge. So what's going to happen is, remember mechanisms, they must show the movement of electrons and in the direction that they are going. So what happens is the nucleophile uses this lone pair of electrons to form a bond with the carbon. So again, draw an arrow from the lone pair right to the carbon, and it's a double-headed arrow because it's the movement of a pair of electrons. Remember, to form a bond, a covalent bond, we need a shared pair of electrons, and the nucleophile donates its lone pair of electrons to the carbon to form a bond with it. And as a result, if you think about what this means for the carbon, if the nucleophile forms a bond with it, it's now going to be up to a total of 5 bonds. Carbon can't have 5 bonds. That would give it more electrons in its outer shell than it could have. And so therefore one of the bonds needs to break. And it's always going to be the weakest bond that's going to break as a result of this substitution, and that is the carbon halogen bond. So because it is polar, what's going to happen is this pair of electrons that originally makes up the carbon halogen bond, which is going to sit slightly closer to the halogen because it's delta negative, that pair of electrons is going to go to the halogen atom, and it will escape and it will become a halide ion, because it's essentially gaining an electron. So what do we then end up with? Well, the halide ion has left, so that's no longer part of the halogenoalkane, and instead the carbon is bonded to the nucleophile, and it's done that using the nucleophile's lone pair of electrons. So you can represent that here. You don't have to draw that in your final product, but just to show what's happening here in terms of the electrons. The nucleophile no longer has a negative charge because it's essentially given away one of its electrons. It had the full share of that lone pair of electrons, so it had the full share of 2 electrons. Now it's sharing those with another, so it's essentially gone down to half of 2, which is 1. So it's lost an electron, and therefore that cancels out the negative charge. And then we've got our halide ion as well, so it's going to be X minus now because it's gained an electron overall. And you can show that pair of electrons there. Again, you may want to show that in the real mechanism as a lone pair of electrons as 2 dots, but just to show that that was the original pair of electrons between the carbon and the halogen. So overall what has happened is that X has been substituted for the nucleophile, and as a result the halogen atom has left with the pair of electrons that was the carbon-halogen bond. And so therefore it has a negative charge overall. So that's your general mechanism, and we'll see that in the first few examples. Sometimes a nucleophile will not have a negative charge, so we'll need to have a think about what that means in terms of our charges overall, but generally this is the mechanism that it follows. And so let's have a look now at some specific examples of reactions with particular nucleophiles. So the first one that we're going to look at is the nucleophilic substitution of a halogenoalkane with cyanide ions. And just to explain what cyanide ions are, I'll draw the structure here. So a cyanide ion is a carbon triple bonded to a nitrogen. There's a lone pair sitting on the carbon and a negative charge on the carbon. Again, you can just draw it as, if you were writing the formula, you'd be writing Cn minus, because really the minus applies to the whole particle, but it is technically coming from that carbon atom. Nitrogen has 3 bonds, so it's happy, and carbon just has this extra lone pair of electrons, which is why it has the negative charge. So you're given the conditions there. So we reflux a halogenoalkane with an ethanolic solution of potassium or sodium cyanide. That is poisonous, so this would have to be done very carefully in a fume cupboard and all the precautions taken. And then we form a nitrile, which I'll show you as our product. You can see the equation there. And essentially the cyanide ion comes in and replaces the halide ion in the halogenoalkane. An ethanolic solution just means that it's dissolved, the potassium and sodium cyanide is dissolved in ethanol, which will be a common solvent for the halogenoalkane and the cyanide. So let's now draw in our mechanism on the next page, on page 19, for this reaction. The reaction mentioned on page 18, which was bromoethane reacting with potassium cyanide. So I've drawn bromoethane here, and it's going to be reacting with our cyanide ion as the nucleophile. So if we draw the structure of the cyanide ion, which is carbon triple bonded to nitrogen with a negative charge, I usually draw it above the carbon because that's really where it sits. But it applies to the whole particle anyway, overall charge of minus. So it doesn't really matter where you draw it, but the lone pair must be on the carbon. You must also draw your partial charges in your bromoethane. So remember that carbon is going to be delta positive. It's electron deficient. The bromine is going to be delta negative because it is more electronegative than our carbon atom. So what then happens? Well, remember with mechanisms, we are forming bonds and breaking bonds. And forming bonds will involve a pair of electrons between atoms. So what we're going to do is we're going to form a bond between our nucleophile and our carbon atom, our delta positive carbon atom. So this nucleophile, which is a lone pair of electrons, is attracted to the electron deficient area of the bromoethane, which is the delta positive carbon. So it forms a bond with that carbon atom. That would give carbon 5 bonds, which it can't have. And so the carbon-bromine bond breaks, like this. What that means in reality is that the pair of electrons that is in the carbon-bromine bond will go completely to the bromine. You can draw that pair of electrons if you wish, but it's not necessary in terms of the mechanism. That arrow is representing the movement of a pair of electrons, and it's the pair of electrons between carbon and bromine. What does that produce then? Well, again, I would always draw what you originally had, which is our ethyl chain. And now connected to that carbon is no longer the bromine, that has been kicked out, but now we can see that it is bonded to our cyanide ion. As a result, bromine has been kicked out. It's now a bromide ion because it has gained an electron overall. And you need to show the lone pair of electrons. So that's showing the pair of electrons that it received from the carbon-bromine bond. It now has a full share of that pair of electrons rather than just half of the share. So let's have a think about the organic molecule that we have produced. I wouldn't recommend you draw this line through your molecule just to keep your mechanism right. But if I just show you here, I'll maybe even just highlight it. When we're naming this type of molecule, this is a nitrile. Okay, and how you name it is you take the longest carbon chain, including the carbon of the nitrile group. So you can see there is a total of 3 carbons in that chain, so the name of this molecule is going to be based on propane. So the start of the name is propane, and then we just put the term nitrile at the end, and that's simply how you name it. So the length of the carbon chain as the full alkane name, so propane, and then nitrile at the end. You don't need to worry too much about naming those molecules. You'll meet those again next year, but that's how you would name that. And this is actually then a method of lengthening a carbon chain. It's a simple method of adding on to a carbon chain and making it longer. You can see that we've gone from bromoethane, so 2 carbons in the chain, to propane nitrile, so 3 carbons in the chain. So in this reaction, bromine Br has been substituted for our cyanide ion, Cn. So that's the nucleophilic substitution of an halogenoalkane with cyanide ions. Mechanism's not too complicated, just 2 arrows all in all. Just make sure you show your delta charges and your full charges as well, and your lone pairs. So let's now have a look at the reaction with ammonia. So ammonia is a nucleophile as well, in the sense that it has a lone pair of electrons. So its formula is NH3, and its lone pair of electrons is on the nitrogen. What's different about ammonia is that it's not a charged nucleophile. It doesn't have a negative charge. So the mechanism is slightly different. It has, just in terms of the charges, because it doesn't have that negative charge overall. But you can see that the conditions are similar. We do it in an ethanolic solution just as a common solvent, but this time we heat it in a sealed metal tube rather than refluxing. So again, we're going to look at the reaction of bromoethane, but this time with ammonia as our nucleophile. So let's have a look at the mechanism here. So here's our bromoethane molecule, and you can see I've included my delta charges, and then we've got our ammonia nucleophile, and again you need to show the lone pair of electrons. So let's see what happens in terms of our movement of electrons. Well, our nucleophile is going to come in and attack the delta positive carbon atom. It uses its lone pair to form a bond with that carbon. Remember that a covalent bond is 1 shared pair of electrons. So it's using that pair of electrons to then form a bond with the carbon. As a result, the carbon would have 5 bonds, which it can't have, and so the weakest bond breaks, and that's the carbon-bromine bond. So that pair of electrons that was in the carbon-bromine bond, you can show them if you wish, that then moves just fully to the bromine, and that breaks away as a bromide ion. So let's have a think about what we produce then. So we've got our just original carbon chain. We'll draw that in first. Then we have got carbon now bonded to nitrogen and 3 hydrogens bonded to the nitrogen. But we need to have a think about the charge on the nitrogen, because it has used its lone pair of electrons to form a bond with the carbon atom. Therefore, it has technically lost an electron overall. So it had those 2 electrons to itself. Now it's sharing them with carbon, so it has essentially half of 2, which is 1. And so therefore it has lost an electron. Therefore the charge on nitrogen is actually positive now. If we think about this from the previous example, if we look at our cyanide ion, it had a negative charge to start with. So it had a negative charge here as the nucleophile. But then when it formed a bond with the carbon of the halogenoalkane, there's no overall charge on it. That's because again, it lost an electron overall, and which cancels out that negative charge. It lost an electron, and so therefore cancelling out the negative charge. So we see this similarly here, but the difference is that nitrogen didn't have a negative charge to start with. So when it loses an electron, it has a charge of +1 overall. So the other thing we need to add to this diagram is the bromide ion that has been kicked out of our halogenoalkane. So we show that as Br minus, it's gained an electron overall, and we show that as the lone pair of electrons. So you can see here that we've got 2 charged particles here, and these can actually exist as a salt as such, which we'll see on the next page. But what can also happen is that the bromide ion, because it has this lone pair of electrons, What it can do, again, remember we're ultimately trying to cancel out those charges. It can actually pick up a hydrogen. Remember that hydrogen can only have one bond, so when this bromide ion uses its lone pair of electrons to pick up that hydrogen to form a bond with it, then it cannot have two bonds, and so this bond to the nitrogen breaks, and that pair of electrons goes into the nitrogen. The nitrogen then gains an electron overall, which cancels out the negative charge. So let's see what we end up with then. So draw your original molecule first. Then we have our carbon bonded to nitrogen, but that nitrogen is now only bonded to two hydrogen atoms. It now has three bonds overall. That pair of electrons that moved in from the nitrogen-hydrogen bond are now sitting just with the nitrogen. It's got its lone pair back, three bonds, it is happy, there's no overall charge on it. And the other thing that we now have is hydrogen bromide as a product as well, because that bromine picked up a hydrogen atom. And we show that, and to be consistent with your pairs of electrons, that bond was formed from the lone pair of electrons that was on the bromide ion, which originally came from the carbon-bromine bond. So in this reaction, Br has been substituted for NH2. What we formed as a result is an amine. Again, you'll meet those again next year. So we started with bromoethane, and now we have got a molecule called ethylamine. So amines are named with the alkyl chain at the start of the name, so it's ethyl, and then amine is the end of the name. So an amine is simply just a carbon chain with an NH2 group at the end, and certainly primary amine anyway. Again, you'll meet that as a full topic next year, so don't worry too much about naming that, but its name is ethylamine. But what you can see in our product here, our ethylamine, is that the nitrogen has got its lone pair back. And so actually this reaction can happen again. This reaction can continue. So this ethylamine molecule could act as a nucleophile, and it could attack another molecule of bromoethane. So if I draw, first of all, my bromoethane molecule, which we had in the first step as well. So if we had another molecule of bromoethane, the ethylamine that we've just formed from step one could act as a nucleophile. We'll draw that, we'll draw our ethylamine, but we'll just draw it the other way round so that the lone pair in our nitrogen is closer to our delta positive carbon. So here is ethylamine that we made in step one, but it's just written the other way round with the NH2 group on the left hand side. So that's going to use its lone pair of electrons now on the nitrogen atom to attack the delta positive carbon atom, and then that causes the carbon-bromine bond to break. What we get as a result is, our original ethane chain from the halogenoalkane, that is now bonded to the nitrogen of our ethylamine, and then we need to draw what groups are attached to the nitrogen. So you can see there's an ethyl group as well. I'll just put that all in blue to show that it came from the ethylamine that we made in step one, and you can see it's also attached to two other hydrogen atoms. Again, the charge on our nitrogen is positive because it's used, it's essentially given away a share of its lone pair of electrons. It's lost an electron, which gives it a positive charge. It doesn't have its lone pair anymore, but what can happen is, because bromide has been kicked out, it has a lone pair of electrons, which it can use to pick up a hydrogen. That hydrogen-nitrogen bond would then break, moving the electrons into the nitrogen atom, giving it its lone pair back and cancelling out that positive charge because it's overall gaining an electron. So let's draw our final product, which will be our ethyl chain from our original halogenoalkane. That's then bonded to our nitrogen atom of the nucleophile, which was ethylamine. So draw the ethyl chain. and then it's just left with one other hydrogen atom, and we show that it's got its lone pair back. Our other product then is hydrogen bromide. And that bond was formed from the lone pair of electrons on the bromide ion that was kicked out from our halogenoalkane. And again, you can see that the nitrogen has its lone pair back, and so this reaction can continue again. It could attack another halogenoalkane, and basically what you would see is this hydrogen would be replaced by an ethyl chain from your halogenoalkane. And then ultimately it will have a lone pair again, and so it can react as a nucleophile again and add another carbon chain on, but this time there'll be no hydrogens to pick up to cancel out that positive charge, so it will just exist overall as a salt, as we mentioned previously, and we'll talk about on the next page. So you may want to write down at the bottom, nitrogen still has a lone pair, reaction can continue, and you could practice drawing that out. So this whole molecule here would then act as your nucleophile attacking another molecule of halogenoalkane, and you should end up with the nitrogen bonded to 3 ethyl chains. So over on the next page, you see a summary of this reaction, and the different substitutions, the amine going on to act as a nucleophile with another halogenoalkane molecule. So you can see we're starting off with our ammonia, that then makes ethylamine. That ethylamine is then used to react with another molecule of halogenoalkane to produce a diethylamine, because 2 of your hydrogens of your ammonia have now been substituted by ethyl chains. That diethylamine still has a lone pair, so it reacts with another halogenoalkane molecule to produce triethylamine. The nitrogen still has a lone pair, so it can attack another halogenoalkane molecule, and another ethyl chain can add on, but this time there's no hydrogen for the bromide ion to remove, and so this is what we call a quaternary salt. There's 4 ethyl chains, so that's what makes it quaternary. And it can exist as a salt because we've got a positive and negative charge there together. That would be called tetraethylammonium bromide. Again, don't worry too much about those names because you'll meet them again when you do your amines topic in A2. So as we said earlier on, in reality, when we have this substitution, even with the primary amine that we form, if you remember that middle step where the nitrogen would have had a positive charge on it and the bromide ion had a negative charge on it, in reality it just exists as that. It exists as a primary ammonium salt. In other words, leave the positive charge on the nitrogen and then have the bromide ion charge essentially stabilising that. In reality, that's what we form, but the mechanism we show that bromide ion picking up a hydrogen and cancelling out that negative charge. So we see hydrogen bromide as a product as well in the mechanism, but in reality we form the salt and then actually need to add an alkali to what we call liberate the primary amine. So we would take our salt, our ethyl ammonium bromide, so that's like the middle step of the mechanism that we wrote on the previous page. React that with sodium hydroxide or potassium hydroxide, and what will happen there is that we'll form sodium bromide because that is a more stable salt. So sodium bromide will be the salt that forms as a result. The hydroxide ion from your sodium hydroxide will pick up one of the hydrogen ions, the H plus ions. They'll neutralise each other and form H2O, water, and that will leave us with just the ethylamine. But again, something you'll meet at A2, so don't worry too much about that now. But in reality, we form the ammonium salts and we need to liberate them using alkali. So we're going to pause there before moving on. So what we've looked at is the reaction of nucleophilic substitution of halogenoalkanes. You should now have an understanding of what a nucleophile is and how it reacts with halogenoalkanes because of that polar bond within the molecule between the carbon and the halogen, leaving the carbon slightly electron deficient. So it's attacked by molecules that are nucleophilic. In other words, they like positive charge. You've looked at the general mechanism and should have an understanding of that and be able to draw that And then we've looked at some specific reaction examples, including the reaction of halogenoalkanes with cyanide ions to produce molecules called nitriles, and halogenoalkanes with ammonia as the nucleophile, which produces amines. We're going to pause there with this video, and in the next video I will cover hydrolysis of halogenoalkanes by reacting halogenoalkane with alkalis. And if you've got any questions on any of that so far, please get in touch.